Good morning, children. Now today we'll start talking about the Coulomb's law. Yesterday what we had done, we'll revise it just in a few seconds. We had talked about charges, its properties, how to produce charges, what is static electricity, and the properties of charges. Now we'll talk about the first phenomenon or the effect which is being experienced by a charge if some other charge is kept nearby. Now that is given by Coulomb's law. You might remember gravitational law which we talked about in class 9. That is universal law of gravitation given by Newton. That was the law in which force between two given masses was explained, and it stated that F is directly proportional to the two masses and inversely proportional to the square of the distance between the two masses. And then a gravitational constant came into existence, which is denoted by capital G, and the formula was F is equals to G m1 m2 upon r square. Exactly in the same manner now we'll also define Coulomb's law. This is an analogy and it will be easier for you to remember in this manner. Now here this force was due to the masses of the two objects. Here the force will be due to the charges of the two objects. Now suppose there are, say, two charges Q1 and Q2 instead of masses, and they are being placed at a distance r apart. Say this is the distance r. Now the electrostatic force of attraction or repulsion. Now the force will be attractive or repulsive will depend upon the nature of two charges. If both are of the same nature, then the force will be repulsive in nature, and if they are of opposite nature, the force will be attractive in nature. Now the electrostatic force is found to be directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two. So now you can see that in gravitational law there were masses, now here there are charges. The other things are same. Now this is electrostatic force. Clear? Now when you combine these two, what will obtain? F is proportional to Q1 Q2 upon R square. And what is this? This is Coulomb's law. And how you can now state Coulomb's law? It states that the force between two charges, say Q1 and Q2, separated by a distance r apart, is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance between the two. Now you also have to remember that Coulomb's law is applicable to only point charges, and that too they must be static, that is at rest. Now as you all know, this proportionality sign will be replaced by a constant if I make it equal to here. So this can now be written as F is equal to, now the proportionality constant will come, will denote it by capital K, Q1, Q2 upon R square. Now this constant K, you can easily find out the units from the expression itself. How? What shall the unit of K here? Now K can be written as F R square upon Q1 into Q2. Unit of force is Newton. This is meter square. Coulomb, again coulomb. So coulomb square, and therefore the unit will be Newton meter square per coulomb square. This is the unit of K. Now what is the value of K? The value of K will depend upon the units in which Q1, Q2 and R will be taken, and it is found out that this constant K can be written in terms of one more constant, which you will now hear for the first time, 1 by 4 pi epsilon naught. This is known as epsilon naught, and how you have to denote it? You make a curved E with a naught here. Epsilon naught. And this epsilon naught is known as permittivity. And when I put naught here, it means permittivity of free space. And what does free space means? It is air or vacuum. Whether the medium is air between the two charges or vacuum, will use 1 by 4 pi epsilon naught, and the value of epsilon naught is 8.854 into 10 to the power minus 12. And now you can see what shall be the unit of epsilon naught. See from here, it will just be the reverse of K, because it will be epsilon naught is equal to 1 by 4 pi K. So it will be just the reverse of K as we had done earlier. So just reversal of that unit will be unit of epsilon naught. I think you can do it yourself. And when you put the value of epsilon naught here, 4 is already a constant, pi, the value of pi is known to you. So the value of K will come out to be 9 into 10 to the power 9. Units we have already derived. I think it must be clear to you. So this value of K will be used up in the expression. Using this expression, you can easily find out the force between 2-point static charges. Now, if suppose the medium is changed, medium is not air or vacuum, then your epsilon naught will be replaced by epsilon n. This permittivity of free space is also known as absolute permittivity. We'll now define one more physical quantity, that is relative permittivity. Relative permittivity. Now, how this relative permittivity is defined? Now, the relative permittivity is the ratio between the force between 2-point charges placed in vacuum at a given distance. 2. The force between the same two charges placed at the same distance in a medium. And this is known as relative permittivity, or this is also denoted as dielectric constant, which you can denote by small d. Dielectric constant. So relative permittivity or dielectric constant denoted by small k. Now what will be the value? So your small k or ER will be equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square upon 1 upon 4 pi epsilon m Q1 Q2 upon R square. This is going to give me epsilon R is equal to epsilon m upon epsilon naught. That means epsilon m is equals to epsilon naught epsilon relative permittivity or epsilon naught k. If I take it as dielectric constant. You can use it as capital A also, and the proportionality constant as small k. That can also be replaced. So how will it change the expression of Coulomb's law? F is equals to 1 by 4 pi. If the medium is different, then k epsilon naught Q1 Q2 upon R square. That means your force will now become 1 by k times the original value. Most of the time, the dielectric constant is greater than 1. So, the value will always reduce by a factor k if the medium is different. Is that very clear? Depending upon the sign of the charges, the force will be repulsive or attractive. Now this was Coulomb's law. The Coulomb's law in vector form will be now done in the second video. Thank you. Now students, will talk about Coulomb's law in vector form. Now why vector form? I told you also in the first meeting that you must be aware about vectors, and I asked you to also revise the vector chapter of class 11. See, Coulomb's law is telling us about the force between the two charges. Now, which type of quantity force is? Force is a vector quantity. That means we can define force, or full information of force can only be given if magnitude as well as direction is specified. So again, now we'll consider the two charges, and now what we'll do, we'll also have to consider whether the charge is positive or negative, because the force on a given charge will depend upon its nature. So we'll do one case first, that is, we can take both the charges as positive. Consider the two charges, say Q1 and Q2, placed at a distance again R apart. Now the force on Q1 because of Q2 will be same as force on Q2 because of Q1 according to Coulomb's law. F is equals to 1 by 4 pi epsilon naught Q1 Q2 upon R square. Now, direction is not specified in this particular case. Now, how to introduce direction in this expression? This is a positive charge. Now, force on these two charges will be now written separately. And how we'll do it? Put a vector notation over here. Force on 1 because of 2. That is force on charge 1 because of charge 2 will be 1 by 4 pi epsilon naught Q1 Q2 upon R square. Now this is giving me only the magnitude. Now on the right hand side also the direction must be mentioned. Now how the direction is mentioned on the right hand side? See, we also have to take care that the magnitude should not change. Magnitude should not change. So what is to be done? First we see what is the direction. See, this is a positive charge, this is a positive charge. So force on charge Q1 because of Q2 will be in this direction. That is from 2 towards 1, or Q1 will feel it towards this side. That is from 2 to 1. From charge 2 towards 1, this direction. So how it is to be mentioned here? Now you can write it in this manner. Unit vector R to 1. The direction is in the direction of vector R to 1, and if this is vector R to 1, I cannot use R to 1 vector over here. Reason being that will change the magnitude. So what I'll use? Unit vector R to 1. This can also be written as 1 by 4 pi epsilon naught Q1 Q2. Now this will also be replaced by R to 1. I can write it like this. Magnitude of R1, this will be equal to R itself as we have done earlier. This can be written as vector R21 divided by magnitude of vector R21. This is an expression for finding out the unit vector. You have done in class 11 that a unit vector A cap can be found out by dividing the magnitude, by dividing the vector by its magnitude. So in the same manner we have done it here. Unit vector R21, you can see this expression now. This is in vector notation. Vector on the left hand side, vector on the right hand side. Magnitude is not being changed, but the direction is specified, that the direction is from 2 to 1. Alright. And here now we have introduced this. R is replaced everywhere by R21. Unit vector is found out in terms of R21. And now this can finally be written as 1 by 4 pi epsilon naught Q1 Q2 R21 vector divided by R21 vector Q. So this is in vector notation. Now force on 2 because of 1 also shall be calculated. Now what shall be the change? Now the change will be, here I have F21. Alright. Now what will the force on 2 because of 1? Now this will be towards this side. So this R will become R1, 2, and everywhere this will be replaced by R1, 2, and you'll get a similar expression for the force, and now you know the direction also. This is the first case where the charges are similar. You can do it for both as negative charge yourself. Now what will be the change if the two charges are dissimilar? One is positive and another is negative. See, distance between the same two charges will be going to remain the same. Say R only. Let me rub off this distance also. Now, suppose this is a positive charge and this is a negative charge. Dissimilar. It can be other way around also. This is negative and this is positive. I will do it for positive and negative. You can yourself do for this negative as well as this positive. Now what is the chain now? Just see. Force on charge 1 because of 2. Because of this charge. This is a negative charge. So this is going to attract it. Now just see, the direction has changed. Previously it was this way. So what will the chain now here? Force on 1 because of 2. Magnitude is going to remain the same. Now the direction is towards from 1 to 2. So I can denote it by as R1, 2. Okay. And this can be changed as 1 by 4 pi epsilon naught Q1, Q2. I can use here now R12 because R12 is also equal to R2. They are same as far as the magnitude is concerned. Multiplied by R12 vector divided by its magnitude, and here also it will be square like this, and this can be written as now 1 by 4 pi epsilon naught Q1 Q2 R12 vector divided by R12 vector and cube of 8. So what is the significance of this? The significance is we can always find out the direction. Now, this is in simple vector form. You must have studied one more physical quantity, that is position vector. We will also be doing Coulomb's law in position vector form. This will be done tomorrow. Now using this concept, you can do question number 1.1, 1.2, 1.12 and 1.13 from your NCERT book. From the first chapter. Alright. In exercise 1.13, I just want to tell you that there is a question that two charged objects are brought together. One is uncharged, another is charged. So the distribution of charge will be equally on both of them. That you have to keep in mind. We had done it on the first day also yesterday. That when an uncharged object is connected with, touched with a charged object, then this charge will be redistributed on both of them equally. So that concept is to be taken into mind. So this is the work for today. You will do Coulomb's law in vector form, and do these for numericals. Tomorrow we'll start with Coulomb's law in position vector form, and if the charges are not point charges, then how will we use Coulomb's law to find out the force between them. Thank you.